Dear ladies and gentlemen, welcome in the Digital Center of Slovenia, Technology for People, as a key business event during Slovenia's presidency of the European Council. In December, we prepared more than 30 events for both general and professional audiences. Under the auspices of SRIP Factories of Future, very rich program has been put together and will be carried out in cooperation with the Ministry of Economic Development and Technology, Spirit Slovenia, DIH Slovenia and BTC, with the main sponsor Yaskava. At this occasion, we would like to remind you to register also for bilateral meetings. But now, I'm very proud to open the Congress and announce today's topic, the role of materials for green carbon-free society. The topic was carried in cooperation with SRIP MatPro, whose focus is on materials, and SRIP Factors the Future, whose focus is on Industry 4.0 and robotics. With such connections, we can contribute to the greatest breakthroughs in the future. Before I give the floor to today's moderator of SRIP MatPro, Simona Knevičević-Bernon from TECOS and me would like to invite you to have a look at the program on the website of the Digital Center of Slovenia and register for further events. But now, Barbara Murn, I give you the word, so please, SRIP MatPro, the floor is yours.
Welcome to the conference, The Role of Materials for Green Carbon-Free Society, that is organized by the Strategic Research and Innovation Partnership, Materials as End Products, abbreviated SRIP MatPro, within the Industry 4.0 and Robotics Month as a part of a program of the Slovenian Presidency of the Council of the European Union. The hybrid conference is taking place here at the Slovenian Digital Center in Ljubljana's BTC City and online as a Zoom event. Our distinguished speakers today are Ms. Antonija Božič Cerar, Dr. Bojan Podgornik, Dr. Andrej Kržan, and Dr. Blaž Nardin. Dr. Jožef Medved will not be able to present today, so we will send you his presentation through email later. We are trying to keep this event interactive, so there will be a Q&A session after the last presentation, so if you have any questions, you are kindly invited to ask them at the end, if you are here live, or type them in the Zoom chat if you are an online attendee. Today is with us also Mrs. Vesna Nachtigal, the Executive Director of the Chamber of Commerce and Industry of Slovenia, who will address you on behalf of the SRIP MatPro, the coordinator of which she is.
Distinguished guests, ladies and gentlemen, I'm delighted to welcome you today on behalf of SRIP MatPro, that focuses on metallurgical materials, metals and multi-components, non-metals materials, and comprises of companies and knowledge institutes recognized for their excellence both in Europe and in the world. Today we will talk about the role of metals, the development of new advanced lightweight materials, the importance of research, recycling and sustainability as potential opportunities for future growth and development. I believe that you will hear a lot of new and interesting things during the next 2 hours, and I suggest that we just listen to them.
The buzzword of today for the future is green, so it's probably no surprise that our first speaker is the advisor to the General Director of the Chamber of Commerce and Industry of Slovenia, Ms. Antonija Božič Cerar, and that the title of her lecture is slightly provocative. Materials Trends in Europe, Circular, Critical, Conflict. Antonija, here you go.
Good morning, everybody. I'm very happy to be here. My role today is to shed light on circular, critical, and conflict materials, 3 Cs. With the new industrial policy in the EU and new trends, we are seeing a reform of how environmentalists perceive environmental policies and how industrial producers perceive producing. With the new role of materials for society, we see that there will be a great need for a great enhancement of materials which are non-agricultural, non-fuel, non-energy in the coming 30 years. The OECD estimates that the need for raw materials will increase from around 80 billion tons globally to 170 billion tons. So this is a huge increase. And why are materials named critical? The EU has had a raw material initiative since 2008. Within this initiative, they developed a list of critical materials. The first one was prepared in 2011, and at that time there were 14 critical materials out of 41 of the minerals and materials which were assessed. In 2014, a new list of critical raw materials was prepared, which had 20 critical raw materials out of the assessed 54. In 2017, the number of critical materials rose to 27 out of the assessed 78 materials. And now we have a list of 30 critical materials out of an assessed number of minerals and metals numbering at 83. So if you look at this map, you can see that the materials that we will need for the future are not equally, are relatively sparse in Europe and also in the North American region. China is extremely wealthy with all of the materials of the future, and actually China is now being called the OPEC, the new OPEC of e-mobility. So they have all the cards in their hands. This is the most recent list of critical raw materials that was prepared in 2020, and you can see, as I mentioned before, there are 30 critical metals and minerals which have been included in this list. That they are critical means that the EU has assessed that they are vital for Europe's economic and strategic development and industrial production. So they are extremely important. And if we look at the list in more detail, we can see that actually there are more materials than 30, because if we look at the rare earth materials, we have around 17 of these, both light and heavy rare earth elements, and the palladium group metals consists of 6 metals. So you can see we have quite an issue in front of us. So we all know that digital supports circular. We also know that there is no use being circular if we do not have low carbon technologies and low carbon energy production. But do digital and low energy actually need circular? If we look at the circular concept as it has been explained till now, it's usually about doing better with waste because we have too many waste streams. But if we look at the technologies of the future and look at what they imply, we see additive manufacturing, which is going to disrupt existing manufacturing, which still consists of heat, beat, treat, to using the optimal quantity of materials which are actually required. If we looked at wind energy and photovoltaics, we see these will be the new sources, some of the new sources for the future, very important. And fuel cells which will use hydrogen to produce energy. Drones are important for both military technologies, robotics for new manufacturing procedures, electric traction motors for new electric cars, energy storage for both storage of energy which we are going to get from wind energy and photovoltaics, and also to drive our new electric cars. And of course we have e-mobility and digital technologies, which are the main enabling technologies for the future. And if we look at these technologies in more detail and we link them to the materials that will be required and to the sectors that we see are the sectors of the future, we see that there is great supply risk. And this is why the EU has compiled this list of critical materials. At the very top of the risk assessment are rare earth elements, both light and heavy. And you see that they are involved in practically all of the technologies that we require for the future. So the answer to my question, does digital and low carbon need circular? The answer is yes, and at a different level than we have been used to till now. If we look in more detail at fuel cells, we see that we have a lot of the materials that were listed on the first few slides. And of course, the base materials are those that we are used to, like aluminium, nickel, and copper. If we look at raw materials used in wind turbines that need permanent magnets, we see that we, again, see a lot of the critical raw materials that were mentioned before. And if we look at traction motors that will be used in e-mobility and electric cars, we see again that we need these critical raw materials. And this is a list of all the materials that are required in solar panels, which will be used both to produce energy here, and also they expect that they will be used in space. And of course, robotics, which will be needed for new manufacturing procedures. Unmanned vehicles, which will be used for military purposes. And as I mentioned before, 3D printing, which is going to revolutionize the way we deem conventional manufacturing. And digital technologies basically can already contain all of the elements of the periodic system. So, do we need circular? Yes, we do. And these are batteries which have already achieved a great transformation in technology. If we look at the old directive from 2006, it targeted collection, it targeted municipal waste streams, because the directive and the measures included in the directive wanted to limit the content of hazardous materials in these batteries, and also remove this waste stream from the streams that were going to landfills and incineration. But if we look at the new batteries and the new technologies, this directive didn't even begin to address lithium. It didn't even mention lithium. It didn't look at the whole life cycle of the batteries. It only looked at the end phase. That's the way we did environmental policies before. But the EU has already made a proposal for a new regulation, which is targeting the new batteries and also the old ones. And it's looking through the life cycle. it's not looking at the end of the waste, it's looking through the whole life cycle. It talks about electrochemical processes, it talks about safety, it talks about greenhouse gas emissions through the life cycle. It also talks about where resources come from, and there is great focus on the materials cobalt, lead, nickel, and lithium. And these materials will have to be collected from the waste stream and recycled, and eventually, after 2025, all of the batteries which will be placed anew on the market will have to contain recycled contents of cobalt, lead, nickel, and lithium. So we are seeing a big transformation on the way that environmental policies are being executed and also how industry production is being considered. The EU proposed a regulation because directives are enforced and implemented by member states individually according to their legal circumstances, but regulations apply along the EU uniformly. This change has been made in order to create economy of scale at EU level, because the EU is aware that we will need new recycling, new collection, new production, which is all capitally intensive, so we will need also funding resources. And then we have conflict materials. Some of these minerals have already been mentioned as critical materials. The EU has enforced this year a new regulation that means that it is applied at EU level, where companies have to verify their sources of tin, tungsten, gold, and tantalum. Because these materials are most oftenly resourced from areas where there are skirmishes, conflicts, there is violation of human rights, child labor forces, and a lot of issues which taint the material stream. So the EU is not the only country which has enforced these due diligence requirements, but the North America has had some rules in place, especially for the Congo region since 2010. And even China is implying new due diligence recommendations. What does this mean for companies? What does this regulation demand from companies? Companies importing metals into the EU have to verify their waste streams they have to verify their material streams along the value chain, especially upstream. So they have to have a management procedure, a policy. They have to address the appropriate issues and have strategies how to resolve these issues if they occur. They have to have third-party audits, and yearly they have to prepare a report on how they perform. Downstream users are a little less involved, but they should incorporate their practices in their non-financial reporting requirements. So, if we sum up, when we began talking about the circular economy in the 70s, Walter Stahel was one of the forerunners. He said that today's products are tomorrow's raw materials at yesterday's prices. But if we look at the issues in front of us, how we're going to collect, how we're going to remove these materials, we see that yesterday's prices is probably not the right answer. There will have to be investments and a lot of effort in future policies and action. Thank you very much.
Thank you, Antonija. Our next speaker, Dr. Bojan Podgornik, is coming from the Institute of Metals and Technology. He will talk about the importance of the advanced materials and materials research for future industry and society growth. Dr. Podgornik, the floor is yours.
Thank you very much. So, to go forward, our biggest challenges today are related to environmental concerns, and this relates to increased pollution, greenhouse gas emissions, global warming, of course, increased energy consumption, very intensive raw materials excavation, and climate change. And so, to sum up this, it all relates to sustainability. And all these concerns have resulted in many different public policy measures, with the latest one being European Green Deal. Europe aims to become the first climate neutral continent by 2050. And of course, to realize all these public measures, actions are required across many different sectors. And this includes increased energy efficiency, use of renewable energy, low emission and carbon-free mobility, minimized material use, then 100% recyclability, biocompatibility, and no waste production. There are, as mentioned, actions are required over many different sectors, with the biggest ones being transportation, industry and production, and energy production. So to start with the transportation, it is a very important sector. It provides 5% of GDP. It gives 10 million people a job only in EU. And as such, it is a very important part of global business and supply chain. But this doesn't come without a cost. It produces 60% of global greenhouse gas emissions. And the biggest part is coming from the road transportation, 75%. It is a significant source of air pollution and noise, especially in cities. It is a major contributor to climate change. It causes urban sprawl, injuries, deaths, and congestions. And while in other sectors, the emissions has dropped in the last 10, 20 years, we can see a big increase in terms of emissions when it comes to transportation. Now, the targets for the next 10, 20 years are the following. EU is hoping to reduce CO2 emissions from the transportation for 50 to 55% till 2030, and that by 2035, all new cars would be zero-emission cars. Of course, this requires low-carbon, zero-emission mobility. Personal cars and small vans will mainly rely on plug-in batteries. Heavier trucks on green hydrogen and fuel cells, while aviation and ship transportation will be mainly on biofuels. To realize that, of course, we need reduced weight of materials, so we need lightweight materials. Another sector is energy, and it relates to electricity production, heating, using energy for manufacturing everything. So in this sector, we will need mainly to focus on renewable energy and high energy efficiency. Looking at the production or release of greenhouse gas emissions, the whole energy sector, it accounts for 75% of global greenhouse gas emissions. And the biggest part, 31%, is coming from the electricity production and heating. Nowadays, still 60% of electricity is produced by gas and coal. The rest is a mixture of so-called low-carbon sources, which is a mix of wind, solar, hydropower, and nuclear energy. The targets in this area are that by 2025, the largest part of electricity generation is by wind and solar. So the 40% of renewable sources in your energy mix should be by 2030. And the overall energy consumption should be reduced by 35 to 40%. So this means net zero energy systems where solar and wind will dominate. The other part should come from natural gas and biofuels combined with carbon capture, some geothermal and nuclear production. In this sector again, we are faced with the problems with the materials. In this case, it is mainly to have excellent materials for transportation, storage, and supply of energy. It is also related to hydrogen, how materials will cope with when being in contact with hydrogen. And then manufacturing. In manufacturing, we have the industry as well as material production. And this is the largest energy using sector. We need energy at every step. So to excavate raw materials, to produce materials from these raw materials, then to reshape and manufacture parts, to assemble the parts, as well as to use those goods. So and not to forget, also to disassemble, to recycle, again, we need energy. So manufacturing, it is responsible for 28% of greenhouse gas emission globally. And we see upward emission trends due to the increased production. We have larger and larger demands on different type of products. Now from this 28%, more than a third of greenhouse gas emissions, it comes from the energy consumption, and then there's some direct emissions like production of concrete. But it is not only the energy consumption and greenhouse gas emissions, it is also waste. It is in the production itself and end-of-life disposal. And in the last 10 years, we see doubling of global consumption. So the trend will just go up. And at the same time, we are aiming for better materials, better products. So we are introducing more energy-intensive and high-footprint materials. Now in this area, the targets are to have more efficient use of energy and materials, which means technology optimization. So better materials efficiency, use of green hydrogen and electrification during the materials production. In terms of technologies, we are moving toward additive manufacturing, lean production, circular design, and recycling. But again, we are faced with the action to move toward novel as well as traditional materials with better properties and reduced CO2 footprints. We see materials are central to all environmental protecting strategies. And the challenges we are facing are to reduce material intensity, to reduce energy intensity, then to enhance material recyclability, to reduce dispersion of toxic substances, to maximize sustainable use of renewable resources, and to extend product durability. And to tackle those challenges, there are certain requirements we need to meet. And this includes reduced weight, so we need lighter materials. We need increased performance, which means stronger materials. We need to reduce power losses, and means materials and surfaces which show lower friction, because the friction is the one which is consuming energy. Then we need materials which resist corrosion and high temperature, so the materials which will work in demanding environments. We need materials with low CO2 footprint and the materials which are fully recyclable. So in one word, we need lightweight, energy efficient and environmentally friendly materials and designs. One way is to go toward advanced materials. These are materials which show novel or enhanced characteristics and properties that cannot be met by conventional materials and products and processes. Advanced materials are also called multifunctional materials, and these materials are lightweight materials, smart materials, nanomaterials, then self-healing materials, self-diagnostic materials, photonic materials, and bio-inspired materials and designs. So it is a broad range of materials. Some examples are polymer composites, metallic metric composites, carbon fibers, carbon nanotubes, titanium aluminides, and shape memory alloys. A special group of these advanced materials are biomaterials and bio-inspired designs, so-called biomimetics. If we look in nature, through the millenniums, nature and living organism has solved many different engineering problems. And why not to use this knowledge? So just by observing the nature, we can come up with some great innovations. Now, looking at the nature, it has, or the living organisms, we can see self-healing abilities. We see self-assembly, self-cleaning, like an example of lotus leaf. And this technology is already used in aviation to coat the surfaces of the airplanes to have self-cleaning ability. Then we have environmental exposure, hydrophobicity and adhesion, like gecko, which can climb on vertical walls on a glass. And engineers were already able to mimic that. Then we have harnessing solar energy and reduced drag, observed in a skin of a shark. And this was used to design swimming suits for competition. Nowadays they are forbidden, but it is an example how just observing the nature, we can come up with some advanced materials. Now we see a lot of advantages obtained by these advanced materials due to specific properties. But we have some sustainability concerns, and these advantages, they don't come without the costs. The biggest are some environmental threats. And these are related to resources availability. For these advanced materials, quite often we need special elements which are not available. Then it is energy-intensive production, quite often high CO2 footprint. We can have problems with degradability and recyclability, some problems with biocompatibility and productivity. And just to give some facts, 32% of plastics produced annually goes into the oceans, having effect on living organisms there. Then carbon fibers, although being like 20 times stronger than steel, their production is 14 times more energy intensive. It produces 10 times higher greenhouse gas emission. And even before the product leaves the factory, 1/5 goes straight into the waste. And also then, it is still 1/3 which ends up as a dump. Then composites can be fully recycled. We can use some processes, but we always lose properties. Then, for example, before it was shown, indium is one of the critical elements. It is the element we need to produce touchscreens. It really made our life easier, much, much easier. But it is the rarest element on Earth. And then lithium batteries. Well, lithium is readily available They can see it for another 200 years. There shouldn't be problems. But since we are moving to our electrical mobility, a lot of batteries will be needed. So there are, it is said that about 10 times higher requirements will be needed, which means 10-fold increase in production, which will be demanding and also much more expensive. Metals, on the other hand, they have excellent sustainable character. Metals like iron and aluminium cannot be destroyed or depleted. Just their location is changing. And metals can be recycled and reused without losing their properties. So they are truly cradle-to-cradle materials. And they can show exceptional properties when produced and processed properly. And when looking at the metals, we can see the potential of metals has not been fully exploited and realized in practice. There's still a lot of room for improvement. For example, looking at steels and materials which are used, or metallic materials used in car industry in the last 10 years, 70% of these materials were not known 10 years ago. So we see a lot of improvements and still a lot of room for progress. And to progress, we don't only need advanced materials, we need advanced materials research, which relates to materials testing and properties correlation, then to measurement uncertainty, modeling and simulation, heat treatment strategies and surface engineering, and materials compatibility. If we start with material testing, industry is confronted with ever-increasing demands on performance, safety, productivity, which means increased requirements in terms of properties of materials. And 10 years ago, the main properties we were looking at materials were hardness and toughness. Nowadays, it is becoming more and more important to follow many different properties, ranging from hardness, toughness, ductility, down to machinability, grindability, wear resistance, fracture toughness, fatigue resistance, biocompatibility, etc., etc. And while we have many different standardized methods to measure all these properties, each of these methods requires specific specimen with a specific geometry, dimensions, and so on. And since they have different geometry, during the production and heat treatment, they may show different properties, different microstructure, and then it is difficult to compare all these properties between each other and to do correlations. One good example of multifunctional specimen, it's circumferentially notched and fatigue pre-cracked tensile bar specimen developed at our institute, which due to its cylindrical shape, it has a very uniform heat transfer. And that's why it has very uniform microstructure, and one single specimen can be used to measure many different properties. Here it's an example. So we can use it to measure fracture toughness, hardness, look at the fractured surface, how it looks, how the fracture propagated, do metallographic analysis, wear resistance measurement, fatigue resistance, nitridability, grindability, compression test, bending test, etc., etc. And in this way, it is not only then to measure properties as a function of processing parameters, heat treatment parameters, but more importantly, we can do correlation between different properties, how one property influences on the other, and then to determine the most optimal conditions to get good machinability, good fatigue resistance, lifetime, and good wear resistance. And when measuring properties, we shouldn't forget about uncertainty, measurement uncertainty. components may have different properties, and this may change depending on the size, surface conditions, loading directions, and rate. And this then, of course, influence also on the measurement uncertainty, which needs to be taken into account, because there may be some defects in the materials which lead to drop in properties. But even more important is the scattering of the results. If we don't take into account the scattering of results, we may end up with some catastrophic failure and loss of lives. So all these need to be taken into account, with measurement uncertainty being dependent also on the environment, number of measurements performed, handling of our specimens, human error, etc., etc. So we shouldn't forget about these facts when pushing for new materials. Quite often in industry it is like, okay, just measure one specimen. If this is okay, it goes. No, we need to take the measurement uncertainty into account. With the development of new materials, of course, we need to know how the microstructure and the properties of this material will change with the processing parameters, with the heat treatment applied, and so on. And to get the response of the material in terms of processing parameters, heat treatment, the one way is to design new tempering and processing diagrams. How this is very time-consuming and quite expensive task. We can shorten that by doing trial and error approach. So we just try different things and we come up with the best solution. But this solution doesn't necessarily mean the most optimal one. We can quite easily miss the best solutions. One way is to do mathematical modeling. For mathematical modeling, we need to understand the physics and chemistry behind all the changes in the material, which is not always easy to do. And we also need a lot of computational time. Better way is to use soft computing methods like genetic algorithms, fuzzy logic, artificial neural networks, and artificial intelligence. And all these methods are able to connect and correlate input and output parameters, factors, without them being in some linear correlation, or even without knowing anything about the process itself. It just uses different mathematical terms to correlate and to find the best correlation between input and output parameters. And in this way, we can do multifunctional simulation and modeling. Here's an example how to analyze the effect of chemical composition and different heat treatment parameters to obtain the best combination of hardness and fracture toughness. So actually, we have like 10 different parameters we vary at the same time. And we can see, we get what is the best way to produce this material, to heat treat it, to get the best combination of properties. The accuracy of these systems, of course, depends on the size of the learning set of data we have. And the larger the set is, better will be prediction and more accurate are the results. And in this case, we really need to be very careful how we use this approach, because if we want to model or simulate something which is outside of the training data set, we may make a big mistake, which again can lead catastrophic failures. So we can only use the range within our training data set. The microstructure of the materials is dependent on the processing and heat treatment. And this microstructure then defines the properties. So it is very important to use proper heat treatment proper processing parameters. The problem is that although also these processes are constantly updated and researched, the latest processes are not known and used in practice. And also, very often, we are too much focused on the bulk properties without thinking about the surface. So, when coming to the heat treatment is an ancient art known and mastered over centuries. In the last 20 years, there was another heat treatment called deep organic treatment, which practices cooling materials down to the temperature of liquid nitrogen or even lower. And although this shows some very great potential, so it shows improving working performance, it improves different properties, it can be used on a wide range of engineering materials in countless applications. It also shortens the production times and improves productivity and quality of the product. It is still not regularly used. It is rather like last chance or problem solver. Also, when it comes to materials, as I said, quite often we are just focused on the bulk properties. But actually, it is the surface which provides greatest benefits. So by changing the surface, we can gain much more than focusing on the whole material. Because surface controls the main life-determining characteristics, like wear resistance, low friction, biocompatibility. So it has also impact on sustainability. It thus reduces impact on the environment. And so we are modifying the surface to perform better, to last longer, and to achieve different functionalities. And this surface engineering can be made by implanting new elements into the surface of the existing material, like plasma nitriding, for example. Then, by depositing surface layers. These layers can be to improve wear resistance, to make it biocompatible, to make it hydrophobic, etc. Or to redesign the surface by texturing, so to differently distribute contact pressure at the surface. So we have seen we need to measure the properties, we need to develop new materials, to properly heat treat it, to model it, but it is also very important about the compatibility of the materials. In terms of green materials and transformation to green society, of course, important is environmental friendliness, biocompatibility, non-toxicity, degradability, recyclability, and sustainability. But material itself, it is very seldom used as one component. We have many different combinations, so we are combining materials to get products. Like a car, we have like 15, 20 different materials we can find in that. And these materials should work together, they should be compatible. And in many systems, we see lubricants, because these systems were designed for conventional metallic materials and to work with these metallic surfaces. Now introducing new advanced materials, quite often we are just keeping the lubricants because they don't only have the function of lubricating the surface, they also have the function of cooling down the whole system, of removing particles from the system. So we need to analyze how compatible materials are with the existing materials and lubricants. For example, some materials, they can show even better properties when combined with certain lubricants, showing reduced friction and wear. While others, when they come, like composites, when they come with certain lubricants, their strength can drop dramatically. So all this needs to be taken into account. We see that for the advanced materials and for the proper transformation into green future, we need advanced functional materials, and we need knowledge, we need computing power and digitalization, we need advanced research and high-tech research facilities and equipment. But even more importantly, it is to do joint research, combining cooperation between universities, research institutes, industry, and government. And one great example is Slovenian cooperative research program Martina, which was running for 3 years, combining 15 partners, and it resulted in development of 3 new ultra-high strength steels for automotive and transportation industry, two new tool steels, new high-strength aluminum alloy, new magnetic material, as well as metallic nanoparticles applied in polymeric materials. So we can see that materials and this materials research is really a key for our transformation to green society. Thank you very much for your attention.
Thank you, Dr. Podgornik. As I mentioned before, Dr. Jožef Medved is not able to attend today, so we will now take a short break for coffee or to stretch your legs. We will continue at around 10:15, so 15 minutes. 20 minutes. Dear participants, welcome back. Our next speaker is Dr. Andrej Kržan from the National Institute of Chemistry. He believes that sustainability will not be achieved without synthetic materials, which is also the title of his lecture. Dr. Kržan, the floor is yours.
Dobro jutro vsem. Good morning to everybody. I will be talking about a statement that sustainability cannot be reached without artificial materials. In today's world of digital technologies, communications, everything in the cloud, we often have a feeling that materials are no longer needed. But I would disagree with that feeling. It is a feeling, but it's not really true. My claim is that we live in a material world, and we will continue to live in a material world. It is different from the way it was in the past. It will change in the future as well, but still, everything around us is material. We can look at examples around us. Life looks completely different. You can remember, how a phone looked. If you're as old as I am, you can remember how a phone looked. It looked like something my children actually don't recognize anymore. You all have a phone like this in your pocket probably, trying not to use it all the time. But it's still a phone, and it contains materials. And it contains different materials, very complex materials, probably less material. You can look at the bicycle. When we were kids, we had the red type of bicycle shown up here. And today you have a fancy bike, looks somewhat similar. It's made of completely different materials. It's electric, it's great, it's fancy, but there are still materials. And we will not lose this, actually. Everything around us is materials. We cannot forget that in our, globalized digital life. There's very often a feeling we're beyond that. We don't need this anymore. We're not beyond that. We can't be beyond that. My suit is made of materials, the podium, everything, but different materials. So since everything around us is made of materials, we're talking about really large quantities. And because there are such large quantities, this is actually a huge footprint of our life. We don't often think about that. We think about, advanced technologies and so on, but advanced technologies are, of course, more material use, different material use. And I would agree that, our use of materials today is more efficient than it used to be. If you just look at this phone back here, it was a big box, and there was nothing in it. I mean, there was one nice thing that you shouldn't forget. When the electricity went, the phone still worked, which does not hold for our fancy phones today. So, there's a catch as well. But still, that black phone weighed like 1.5 kilos, I think. My parents have one at home, actually. I know how heavy it is. A lot of material, very inefficient material, and a lot of metal. If you remember, old radios, that was like a piece of furniture. That was like a big wooden box. The producers used to have a carpentry shop to make radios, which is crazy today. Then you would look inside, and it was on a nice metal piece, was heavy, and so on. Today a radio is almost pointless. It's a small thing, as small as you wish almost. I can run the radio from my phone, or have it in my pocket or in my earphone. It doesn't really matter. So we're using a lot less material to make the same products very often. A lot less. But we have a kind of interesting situation that we're using more materials. We're using more materials despite our very, very efficient use of materials. And this is something that is a challenge for us. More materials because many things that didn't used to be a commodity are today commoditized. They're bought, they're thrown away. Clothes are a typical example of that. Fast fashion, we all buy literally tons of clothes that we often don't wear and then actually get rid of without even wearing it, and most certainly without using it to its life end. Because, well, we don't like it anymore. Maybe, like in my case, we grow in certain directions, so it doesn't fit us. Or it may be just not fashionable. It's not the right color, so we throw it away. And that's actually where we produce really a lot of waste. So we're producing a lot of materials. We will continue to produce materials. We're producing a lot of materials, possibly more than in the past, and we're discarding them very, very quickly. Something that's new about the materials that we use and in the way we use it is that we think about sustainability principles. That didn't used to be. This is a comfort that we have today. We can think about it. We have the knowledge to think about it. Concepts such as efficient material or resource use weren't actually mentioned in the past. Recycling was never mentioned. It was part of life because resources were difficult to obtain. And the further you go in the past, they were more difficult to obtain. So nobody in their right mind would ever think of discarding them. If you go to the Bronze Age, bronze was extremely valuable, so of course it was recycled. We think recycling is something that we've invented. That's not the case at all. That is not the case at all. We are doing it because we understand the limited nature of resources and that we can consume more and extract more than is available. And we're reaching these limits, let's say, with critical elements, which is actually a real issue. My colleague, Dr. Podgornik, mentioned it with indium, I think. We can make all the touch screens we want, but where are we going to get the indium? That's an issue. And if I just look at this picture here at the bottom behind us, you know, people say, okay, we're using a lot of plastic. This is the use of plastics through the years, and I think it goes into the future. It goes till, I don't know what year, 2050. We're somewhere in, oops, not laser. Well, we're somewhere in the beginning of the dark blue part. We think, you know, the growth of plastics goes exponentially. And, well, it cannot continue that way. It can. And the prediction is that it will, okay? So, I will focus on non-metallic materials. You've heard a lot about metals and the general principle. I will talk about materials that are non-metallic. We call them multi-component within our group. And I'll try to show where we're going with that and what to expect and their importance. Okay? Like this. No? Did I do that right? Okay. And I did something else now. Okay. Sorry. Back and forth. So I'm talking about plastics. I'm talking about non-metallic composites, and all of these materials are multi-component materials. They have a simple one name, but in fact these are mixtures of materials. That's why they're multi-component. Even plastics, we always think it's a homogeneous material. It's not a homogeneous material. It's based on polymers, and then we use all sorts of fillers and all sorts of additives that make a material that we can actually use and produce products. Similar with composites, we have a matrix within which we have reinforcements, fillers, all sorts of additions, so that we get a useful material. The components by themselves have a very, very limited use. So that's why these are multi-component materials, all of them, actually, without us recognizing it. And of course, if you have several components, or a number of components, not just several, that you're mixing, one option that we have, and something that's happening, is that we can make new combinations. We combine different things, possibly in different ways as well, and that leads to new materials. So many of the new materials that we see today have very familiar names. You know, they don't tell us about all the grades of, let's say, polyamide or nylon, if you wish to call it. Okay? There are many nylons. People just say nylon. There are many nylons, so polyamides by themselves. And then, of course, we have these little improvements that are reached through advanced combinations. And here I have a picture of an oil sump, you know, on a automobile or truck engine. I think it's an automobile in this case. So the bottom of the automobile engine, where the hot oil is and the oil pump goes. This never used to be made of plastics. Well, today it is. It is. It's a polyamide, but of course it's an advanced form of polyamides. So this is how new materials are creeping into our life. Very often, small incremental changes, but in fact, new materials with new properties, new application possibilities, and in fact, really new materials. Another component is the bio aspect coming into materials. Artificial materials are often seen as something completely distinct from anything bio or anything natural. Well, this is no longer so. And again, we're going in an incremental way. We have materials that are exactly like made from, through the artificial route, that can actually include bio-based components. So we can have polyethylene that is bio-based, and it comes from sugar cane, ethanol, and so on, and is chemically exactly identical in this case to something that we make from fossil sources. So what I'm talking about is the inclusion of bio resources and basic components, or basic raw materials that go into the production of the material. Of course, it doesn't have to be exactly the same as in polyethylene. It can be slightly different. So we're adding biocomponents. Maybe, a polymer like an epoxy resin will have, 2, 3 components that make the resin, and we can exchange one with a slightly different bio-based component. So all of a sudden, the epoxy resin, that has nothing to do with nature really, contains a component coming from nature. It's bio-based. And of course, this can extend all the way to 100% with different materials. And that is in fact what industry is doing. They're trying to find bio-based components that fit into their existing products with very minor modification. And this is another creeping change that we don't feel, but is happening. So when you buy your paint, your varnish, it will contain already some natural components. It didn't used to be so. And this is going on and on. Let's say, serious producers such as, Airbus, making airplanes, is switching epoxy resins to nature-based components. So when you'll be sitting on a plane, a completely non-natural structure, it will be made partially from natural materials, and much more than any of us expects. And those are in fact new materials. And this goes not only for the components, it goes for the function as well. As you're moving toward the natural side, you can get materials that are biocompatible. So you can go into the idea of biomedical applications, and you can have stents in your body, you can have all sorts of parts in your body that are artificial, and they can be compatible for a long period or a short period. They can resorb. So for example, you will get a plastic screw in your hip, and it will miraculously disappear, so you will not need a second surgery to extract it, or you will not beep when you go through the metal detector. And these are small things that we take for granted, and they happen daily, effectively. Then we have, of course, biodegradable materials, another aspect of bio. So the material, once it becomes waste, will be, let's say, consumed and absorbed by the natural cycles, material cycles. New materials can be, of course, quite different as well. I mentioned here vitrimers, polymer networks that are reversible. So you have a plastic material, let's put it, that is normal as we're used to it, and then when you apply stress to it, let's say in the form of temperature, it will liquefy, change form. So you can recycle it, not like a thermoset, which is cross-linked, and unfortunately you cannot recycle it easily. So we have thermosets that can be recycled as thermoplastic polymers, which is a great improvement. And this can be used, to have a material that offers stress relief. It can be shape memory materials. It can self-heal. So you have a material that develops a crack and will self-heal. I mean, how great is that? And how efficient is that? Because your product will not become waste. You can still use it despite having a crack in it. That's great. That's very efficient and very sustainable, in fact. And of course, you can have a material that's really easy, designed to recycle. What is also included in new materials can be sensoring. So you can see when a material is degraded. Here you can measure it, you can see it sometimes. You can sense if a material is getting to the end of its life and, let's say, fatigue is becoming a problem. So you know when to exchange a part on an airplane. You don't do it just by, some routine. Every 2 years we exchange this because it has so many flight hours. No, you can see, is it at the end of its life and needs to be replaced or not yet? This is efficient as well. You can add functionality. For example, you can change the material of an airplane again so that, for example, you don't need to defrost it. It will not adhere water or less water, and it will inhibit the freezing of water. So you don't need to de-ice it. I'm sure you were all sitting on planes, and waiting to be de-iced at some point. Less now than before. It can also include comfort. Let's say in textiles, you can have clothes today, fibers that contain a component that will exchange heat. So when you're hot, it will cool you. When you're cold, it will retain heat for you. And not like wool, not in the same principle. You can have a phase shift material included, and that's in fact the case. So you will be comforted as well by it. Okay? So we're having a lot of new materials coming effectively daily, and this is continuing, and it's actually exciting changes. We also have new processes, how to process materials that are reflected in products. The starting point is already, a very high benchmark. If you look at plastics, they have unsurpassed production speed and cost efficiency. That's what makes plastics so useful. You can produce products very, very quickly at minimum cost. That's why we have so much plastic everywhere. I'm involved in a company that makes something from plastics, and we're often asked, well, why don't you use something else? And I ask, okay, what? What? I mean, should we use wood and then sit there and carve the piece out of it, like in the olden times? Or should we use metal and cast it and use really a lot of energy to do it? There is no good alternative to plastic in many, many, many products. And this is continuing, of course. I mean, plastics offer, to avoid coloring, painting. If you make something of wood, you'll probably have to paint it and protect it. Plastics already has a pigment. You don't need to paint it. You can add structures on the surface. You can print on the surface in the mold very often. So a piece falls out of the machine, it's finished. And in cases, where we again don't even recognize it, we're holding plastics, like this door handle up here. These chrome handles and chrome pieces on our cars, for the most part, they're not metallic, they're plastic. It's chrome-plated plastic. This is a process development that we didn't used to have. Looks like chrome, looks like perfect chrome. It's only when it breaks and you look at it, you go like, oh, this was plastic. Didn't used to be. Then, for example, if you have a cool motorcycle, there's a Slovenian producer that makes rims for motorcycles made of composites. There's not a piece of plastic there. I mean, piece of metal there, as it used to be. This is not like some light alloy and so on. No, it's a composite. And it's in our life today. And this is possible because of advances in the production. Let's say for composites, since composites are really very, very interesting materials because they offer great properties at very light weight for the most part. For composites, production is a major bottleneck. But here you can see, for example, a robot putting together a carbon fiber reinforced panel for an airplane or for something big. That's possible today. It didn't used to be. Once we overcome this hurdle, then a lot of products can be made in a serial production out of these kinds of composites. That's a bottleneck that we're overcoming. Then, of course, we can include recycling and waste management, waste treatment, as a process development. Recycling is being improved. Probably you're not aware that recycling is moving from something that used to be called mechanical recycling, where you would take a plastic, melt it, and make something else out of it, and leads, in the most cases, to downcycling. So it's being replaced by so-called chemical recycling, where you take a polymer, or plastic if you wish, and you decompose it, you depolymerize it, you can purify the product that you get, and then reuse it to make materials that are exactly the same as virgin materials. So you are moving toward an infinite loop, which is exactly what circular economy wants to be. We're not there, but we're going there. You can use pyrolysis, for example, to decompose composites, like fiber-reinforced composites, and you can get all the components out again to reuse them. In Ljubljana, just actually not very far from here, is a chemical depolymerization of nylon 6 to make new fibers. It's very efficient. It can use old carpets, old fishing nets. It's done here. It's done today, and this is actually where we're going. That's where the future lies for us. And it's efficient, I hope, and sustainable as well. Another point of sustainability, a large part, is actually connected to fuel efficiency. And when you look at light weighting of vehicles, all types of vehicles, that we move around with, we can see new materials taking place there and having a major role. Weight reduction is the key for lower fuel consumption. And this can be true for you going biking during the weekend. I know there are some biking enthusiasts here, and I think you might recognize, or at least you will know, that having a really cool and light composite bike is great. It's lighter, and you can do a lot more, go to the top of every hill and go distances. Well, the same holds actually for automobiles. If two people can hold a whole shell of an automobile, well, obviously it's not made of metals, and it's going to be very light. You will use less fuel to move that, or you can possibly use electric propulsion because, well, you have a light car. As I said before, one of the shortcomings here is serial production of these. Same holds, for example, for airplanes. There, the development has been really drastic. I have a graph up here of Airbus planes, I think, and from the 1970s, the content of non-metallic composite materials were approximately 5%. Today, we're above 50%. So new planes are more than 50% made of composites. And I'm not saying that composites are superior in every case, let's say, to metals, but in many cases they are. For example, you don't have a problem with corrosion, which can be, let's say, a great advantage if you have a wind production facility out in the North Sea. Corrosion in salt conditions is killer. You have to go and exchange the metals if they corrode. If the composites don't corrode, well, you don't have to. And we have a lot of sustainable applications. We have, new sustainable technologies, but again, what are they made of? What are they made of? And when you look behind the scenes, number one, of course, it's a lot of material. It's some fancy new materials. And very often you see, it's polymer-based materials. Let's say wind power. The blades of the windmill are made of composites. That's it. And they can be today, let's say, more than 100 meters long. We have a facility, a producer in Slovenia that makes these blades for major producers, actually. And the last time I was there, they were working on a blade that was 103 meters long. They had huge problems moving the thing. Made of composites, one piece. Quite difficult to do, actually. If you look at flexible solar cells, well, they're flexible. What are they on? They're on plastics or some sort of a fancy plastic, possibly. Without that, you can't make it. You can't use glass and metal to do that. That doesn't work. If you want technologies that have a low energy, or actually that are light, I already mentioned, that are, have a smaller weight. But even, if you want light, something that crept in our life are LED lights, like this strip down here. I think we all have them at home now, or at least our kids have them. That's all plastics and polymers. Unfortunately, a difficult to recycle product. I think they haven't solved that. But new materials everywhere and low energy consumption. And if you want to reduce your energy use, well, you use LED lights. That's what we do. It's a contribution to our sustainability. It can be also for low energy use in that sense. It can be low maintenance, like I mentioned, the prevention of corrosion. So if you don't have corrosion, you will have less maintenance. You don't have to sit there and paint the thing every 2 years to prevent corrosion or exchange a part, so you can have a longer durability. Very efficient. It also improves our lives. That's sustainable too, I think. That our lives are better in the sense of health or medical devices. You can have a stent in your blood vessel, or, which I find, absolutely amazing, that we can use composites and advanced materials to enable people without legs to run, to compete. I think that is fabulous. I think that's the most amazing of all these applications here. Hard to believe, I would say. It looks like from a movie, and it's not from a movie. It's from somebody's life, making their life much better. And that's happening, and there are many examples of that. Or if you want, in today's world, we're using masks. I have the privilege, since I'm standing up here, I'm not having one on my face, but everybody else that I see does. That makes it possible. We can prevent the spread of disease by something as simple as a mask, although, again, we're going in the direction of single-use plastic and a lot of waste, which is still a challenge. Waste is a challenge. And we have to look at waste treatment and better treatment and use of resources from two sides. One is to reduce the environmental burden. So we don't have waste everywhere. We don't have the plastic patch in every ocean. or that you don't have plastics lying on every beach where you go. It's really annoying, it's ugly, and it's not good for anybody, not for us, not for any other organism, not for the ecosystem, and not for our future, not for the future of our children. But it's beyond that. It's not just like environmental pollution that we're talking about. There's a technical view of it. We have to realize the benefits that we get from good waste treatment. And new materials, like I've given you examples already, allow us to use the materials again. So the waste really can become a source of raw materials, or let's say already have finished materials, where you can recoup the investment done already in the production of those materials, as is so famously done, let's say, in the recycling of aluminum. But aluminum is not the only material that has a high energy input and can be recycled efficiently. Carbon fibers from carbon fiber reinforced composites also have a high energy input, and they can also be reused if we do it properly, and that's the direction we're going in. So we have these two aspects. One is that we're preventing the burdens and saving the environment, but we're making the process much, much more efficient, and we get a source of material. So hopefully we're not going to run out of that indium. This, of course, has to be an integral part of material R&D, and I believe it is today. But of course, also, it should not be an excuse for greenwashing. I hope that we are all knowledgeable enough about what really is sustainable so we can actually identify greenwashing and also call it by that name when necessary. What are we doing in Slovenia? Well, in our strategic partnership, we are focusing on multi-component materials. These are non-metallic. We have a section that works on metallic, and you've heard about that, as well as technologies. 3D printing or additive technologies, for example, but also all the recycling options, like from chemical depolymerization and so on. Materials are a significant part of the Slovenian added value, exports, and GDP. I have some numbers here. I think they're quite impressive from 2020. So it's 822 million euros of added value, 3.5 billion of revenues, and 2.5 billion of exports. These are quality jobs. So we're going, not from the environmental sustainability, we're looking at the economic and social sustainability, people having good jobs, salaries, the economy working, and this also has a strategic importance. Materials, I hope we understand, will be produced. The question is, who will produce them and where will they be produced? It's jobs and the economy. And we need to have those things. Not that this is all farmed out somewhere else. We have to do it efficiently by ourselves. So it has a strategic importance. And this is a competitive and strategic advantage that Slovenia has in certain areas that we must continue developing. There are two products here, just since they're big and easy to identify, that are made in Slovenia. They're high-tech, they have high values. Not everybody can make them, but we can. Our industry can, and they're based on materials. So we have to keep that. Two things that I think in the future will steer materials. One is digitalization. There's a great potential here, which I don't actually fully understand. I hope I appreciate it, but I don't really understand it. And I think we will need the input from the IT industry. Things like IoT, blockchain. This will be a huge part of the Industry 5.0 or I mean 4.0 or 5.0 when we get there. And another thing that I really, really believe in is the merging with the natural world. Our materials will be merging more and more with the natural world. So molecular biology is not something very distant actually from materials anymore. And part of this will be mimicking, but it will also be completely new materials, functionally and still natural. If we just take the examples, I mean, I love, for example, the structure of a squid bone. It's great. It's made of organic and inorganic. It has an intricate structure. It's lightweight, and it does what it does perfectly. And we cannot make it. We don't know how to make a structure like that, to be honest. Or, if you want, an even more trivial example that we burn very easily, take for granted, is wood. Wood is a natural structure. It's biodegradable. But if you use it properly, it might last for 100 years, let's say in the roof of an old church. So how is that? And it has a very intricate, very fine nanostructure, although it's huge. We cannot make that. We don't know how to make such a great composite as wood. So this is something that's in the future. And I think we can look at structures like DNA containing information. Wow. So we can have natural materials that are structurally unique and something that we can't make yet, and then add information. That's digitalization as well. So I think we're going to go in that direction with really synthetic materials that will be at the same time completely natural and will mimic nature. And I think that's where we're going, and I'm really excited about that. Okay? No? So I hope that I've given you sufficient evidence to convince you that actually materials and synthetic materials are necessary for our sustainable future. And that's where we're going. Thank you very much.
Thank you, Dr. Kržan. And now, last but not least, a very important topic, human resources. We need educated, competent, and agile employees, both in industry and in the knowledge institutions. Dr. Blaž Nardin, the Dean of the Faculty of Polymer Technology, will share with us an insight into education for a sustainable future. Dr. Nardin will be joining us through Zoom.
Yes, hello everyone. I hope you can hear me. And I will try to share my screen now. Just a second, please. So, okay. So, hello, my name is Blaž Nardin. I am the Dean of the Faculty of Polymer Technology. And my today's role is to show you the education for the sustainable future. And with that, I would just like to thank to my colleague, Andrej Kržan, who just explained a lot of parts, or I would say he explained more or less all the topics which are needed in the educational institutions for the future of the sustainability of our planet. So looking at this, I was amazed when I saw the graph when Andrej predicted the usage of the plastic material by 2050. I'm not able to predict it in such a long period of time. But what I can say that until 2035, we are sure that it will be the consumption and the production of the plastic material will be doubled. And with that, we will come to 2035 to approximately 650 million tons, and Andrej predicted 750 million tons. So we are very close, but you know, it's the point here is there will be material, as Andrej said, there will be a processing of the material, and there will be a usage of the material. And therefore, we have to ask ourselves, what applications are there? Andrej explained a lot of them, but looking from the structural side, I prepared this picture. It is sourcing from the European Strategy for Plastic in Circular Economy. Approximately 40% of all plastic materials still goes to the packaging, and therefore this material is then, you know, somehow wasted, and this part definitely needs to go to the second, third, fourth, or infinitive loop for the recycling of the material. Approximately 20% of the material goes to the construction works, where we can say in a lot of applications these materials are more or less sustainable because they will last for 50, 60, 70, 80 years. So there will be more or less a long period of time when they'll be in use, and there will be no damage to the material, and they will be in constant use. For the automotive, you can see currently 9% of all the plastic material in Europe, this data is for Europe, is used for automotive applications. And if you would take a look at the trend, we would see that this trend is going up, and I will speak about this a little bit later. Electronics, 6% goes for the electronics. So there are many applications where we can see that plastic materials are used. And we didn't even speak about aviation, wind turbines, solar power, medical application, and so on. So there are many applications, and we know and we are sure that all this industry is very important and needs educated students, needs educated professionals, and needs trained professionals, so that we will keep the jobs here in Slovenia, so that we will keep the jobs here in Europe, and that we will be competitive on this side. Due to the fact that I said that approximately 40% of all plastic material goes to the waste, immediately comes to the question, is this a problem? Somehow, yes. We can say it is a problem, but let me see what was already done. The ban of single-use plastic. That is a good point, because we have alternative solutions, and I think it's good that we use other materials which are more sustainable than plastic materials for the single-use product. And this is up to our habits. When I was thinking why we are really using so many products, what is behind that? How can we decrease the consumption of the material? And I said one possible solution, or I think the only possible solution, is we have to change our habits. We have to stop driving the cars. We have to stop using airplanes. We have to stop using all different things which we are using currently today. And if we will do this, then of course the consumption of the material will go down. Of course, the consumption of the material will go down. But are we ready to do this? Honestly speaking, putting the mirror in front of ourselves, I'm not very sure we are really honest that we will do this in the near future. So therefore, let us see what has already been done. So the collecting of the industrial waste plastic, it is in progress. We can say it's done, because in vast majority of the companies which are processing plastic material, they are recollecting the industrial waste, and they are reusing it, because they can do this very fast and very efficiently, and it is without the cost. So this is already done. The reusing and recycling of the plastic materials, which is coming from the homes, it is in progress. We are not done there. Too much material is burned. Because it is a kind of at this economical stage, it is very economically that we burn these materials. And what is on our side, on the educational side, we have to find the methods, we have to find the solutions, how to recycle this waste material which is coming from our homes. Upcycling and recycling of plastic materials, it's going on. So how to improve the plastic materials which are coming from the waste? Andrej previously said every material is a composite. Yes, definitely it is. And we just have to find a way how we can upgrade it to come back to the properties of the virgin material as it has the material at the beginning of the usage. Using biodegradable, bio-based material. This is another point, another area where we can see a lot of solutions for the problems which are having today, and of course development of new recycling solutions for all types of plastic material, not only for the thermoplast material, where we have very good results, but also on the thermoset materials, which are more problematic for the recycling. So what I'm saying, the plastic is not a problem. In fact, the plastic is solution. I would say that not only that the plastic is the solution, I am sure and I'm convinced that what is the job of the science, what is the job of the future engineers, is that they find the best possible combination of the material for every single application. So I am not saying that plastic is bad material, or the metal is bad material, or the glass or the paper, or any material that is bad. No, we just have to find the usage of it, and we have to find the best possible application and the combination of the materials. So maybe one more word about why has plastic, the broader audience, such a bad reputation? Because plastic can flow, or most of the plastic flows on the water. So we see the debris, we see the waste, and we see all this pollution which is going on. But this was not done by the material by itself. It was done by human being, by us. So we put this material somewhere it should not be, and it is us to blame, not the material. So for the educational purposes, what is very important? We will have, or we already have, new materials. We have to teach our students that new materials are there. They have remarkable mechanical properties. They have remarkable chemical properties. So there are many, many different new material, and it is up to us to teach them which material to use where in which application. And you can see that also the teaching methods are very much different compared to the 1940s, when there was a classical classroom teaching. Currently, today, we have a lot of teamwork, the educational process. We have a lot of project work. We have a lot of creative workshops, and so on and so forth, which shows the possibility that we come from the old design of the cars, which were able, with the technology and the materials which were done in 1950s, to the new design and new functionality of the materials which we are having currently today. So I will not discuss these good and bad materials. You know my answer, and my belief is that there are no good or bad materials. There are just materials, and it is up to us to find a way how to design the product, how to use the best material for the application. And what is in fact the sustainable future for us? We saw today that everybody have to take care about the usage of the material. Use the material or use the product as long as you need it. And after that, the designers, it is up to them that they design the product which can be recycled and which can be then, of course, also reused. Currently, today, we have a lot of applications where, and there is with a it's very hard to understand why there are such designs which are very, very difficult for the disassembly at the first site, and on the other side also for recycling. But I think that we are going in the right direction. So the design for disassembly and reusing is one of the topics which must be very much involved in our educational process. What are the strategic goals for the higher education, for industry on higher education? Industry needs to get the talented students to the higher educational institutions. So it is up to us, everyone, to all stakeholders, that we make the technology, we make the material science, I will say, sorry for that word, but I will say sexy. We have to make it really attractive, and that we get the best and motivated, most talented students to our faculties, because they will be able to create new applications which will be innovative and which will give us also to the industry, of course, the needed added value for the sustainable production. So the graduates needs to be fit and for the challenges of the future, which is rapidly changing environment. We see the political world is changing, we see the habits are changing, and we as an educational institution, we have to be ready, that we already teach our students how to adapt to this fast changing environment. And to get the graduates to be able to conduct applied research, not only the theoretical, but the engineers which are coming from the higher educational institution, they have to be applicable, they have to work on the projects, because when they come to the industry, they should be very much practical oriented, and they should know how to work in the industrial environment. And so with our infrastructure, which we're having at the higher education institutions, we have to give to the industry appropriate infrastructure for further development. And we have to support the industry with the infrastructure which we are having, and therefore give them as much support as they need it. And of course, at the end, the industry and the higher education institutions should give the value to the local communities as well. So in the future, the challenges for the engineers, as I said, fast changing environment, technology is changing from day to day. Half a year ago, or maybe a little bit more, 5G started. Before that, nobody knows really how in the industry, how this thing will work. Now we have the technology here, we have to adapt it. We have to be ready that we will have all the data available all the time, wherever we will want. Why is that important? Because then we can monitor our processes in the industry on time, not with a delay, and we can immediately see if there is something going wrong, and we can, with the 5G technology, we can also adapt the process where it would be needed. We are not there yet, but with this support of the technology, I'm sure that we will be there very fast. And if you take a look 3-4 years ago or 5 years ago, everybody was really curious about using of the mobile data on our mobile phones. Today, nobody cares at all what is the mobile data. So because it's coming infinitive, more or less, so we can use it. We have the data, but currently with the 4G or 3G technology, it is not fast enough. But 5G gives us this opportunity that we can monitor our technological processes within the industry on time and real life, and we can do it if the technology also at the industry is ready. So that if we are speaking about plastic processing technology, for example, injection molding technology, if it is equipped with the sensors and actuators, then we can monitor and control it online. So these are a kind of challenges for the production types in terms of Industry 4.0, and the working environment is changing from the local to global. You know that all the production facilities are more or less distributed due to the fact that we cannot produce everything on one single space, because we are limited with the human resources, we are limited with the energy resources, we are limited with the material resources, and therefore we have to be able and we have to be adaptable to work in the multinational environment. And so with that, we have to also understand other ways and cultures, and we have to train our students to be adapted to this, and that they could be able to work in the different industrial environments. And what is also very important, shifting from the linear to the circular economy. I think this is one of the major issues at the higher educational institutions who are dealing with the technology and the materials, that we train the students, that we have to go from the linear to the circular economy. What are the required competencies for the 21st century students? They have to be, if they want to come and if they want to prosper in the industrial companies, if they want to have good careers, they have to be self-initiative, they have to be curious, they have to be ready to have a constant learning, they have the ability to be creative and not only creative, but also critical thinking. So to see if this is really okay, to challenge themselves and challenge the team in which they are working, if they really have the best possible solutions. They have to have effective communication skills. They have to do entrepreneurial thinking, because this is also maybe one of the fields which was very much neglected in the past in our educational system. We didn't push our students too much to think also in the entrepreneurial way. The teamwork, I think today on most of the faculties, which I know, this is not a problem anymore. So the teamwork is really well introduced. And of course, knowledge of the foreign languages, I will not even speak about this. Interdisciplinary thinking, using and merging different knowledge in the creation process, and understanding the meaning of the sustainability in circular economy. I think this is really, and I will repeat this many times. And all these points are listed in different national, international papers, statements. I think we have now here for that high agenda, and from the higher educational institutions, we have to go in these directions. So we have to develop, as a higher educational institution, we have to develop new concepts and new types of study process. We have to train and motivate also our teachers, our professors, our assistants to use different information communication technologies, so that they will have the materials ready in a new way, because the new students who are here, who are already at our faculties, our universities, and the new generation which are coming, they are different, and they think different, and they look at our world differently as we do. So therefore, we have to adapt our teaching processes and our teaching materials to the new technologies, and with that also sometimes, and in many cases, also change our study plans and be very much fast. We should be very fast in the adoption of the requirements from the industry. And last but not least, the classrooms and the laboratories needs to be equipped as well, so that the students will have all the technology needed for their work. It was for me very interesting to see this map of the world, and we can very fast see where is the very interactive. This is the dark blue areas. You can see here North America, northern part of Europe, Germany, Benelux, Australia, New Zealand, when there is a very high integration of the interactive schooling system, and the lighter color it is, the less interactive educational processes is going on. So we can see that more developed economies, and more developed societies, not only economies, they are using really interactive teaching system. And for that purpose, I'm sure and I'm convinced that there is a very big connection between way of education to the success of the economy and the society. In the framework from the World Economic Forum, in the Forum for the Education 4.0, which is a kind of support to the Industry 4.0, this nice picture shows us how the merge of the content-wise, so what is needed for the experience, what we should have is seen from the global citizen skills, innovation and creativity skills, technology skills, and interpersonal skills, how to merge all these content-wise, what is needed, to the experience, what we can do, what we can feel from the personal and self-paced learning. So to adapt the learning process to the students level, to be accessible and inclusive learning, so to involve the students into the student process, problem-based collaboration learning, and lifelong learning or student-driven learning. So from that vision, which is written here, and I really much agree with it, is that also the teachers, we professors who are working at the higher education institutions, we have to be ready to be to include the students to our teaching process, and that will bring us a lot of work, because we will have to change our current way of work. And there are many results on the higher education studies. What should be done and where should be done. I already spoke about this. I will just maybe point out some of just few of the facts here, that there are new generations who are of the students who are coming. They are very much different, and we have to adapt to our study process to them, because somehow they will they are used to a different approach, and we have to come closer to them and give them as much as possible motivation. But still, at the end, they will have to study by themselves, because the study process is, of course, at the end still very much individual work, because everyone and each and single student should have his or her own personal work which needs to be done. That means he or she must do her homework and study the very heavy content which they have to understand, and we as a teachers should give them the support for the understanding of the content. There are also there is also a lot of materials based on the EU agenda. What is new? The main point is to eliminate inconsistencies in the knowledge in EU between what is needed and what is reality. So the theory and practice, there is a big gap in between, and we as a higher education institution, we have to make the bridge between those two banks and link them together, so that the students will get really good knowledge. And to say maybe one more thing, that also currently also in Slovenia there is a new national program for the higher education in the Republic of Slovenia for 2021 to 2030 is being done, and it is the really final stage, and I hope this will bring us many new and good solutions for the higher education itself, as well as for the industry, as well as for the whole community. There I will go to some practical works, to practical examples, where attraction to the students and pupils already in the early stage, where we have to make a promotion for the material and science and technical studies and technical professions. We have to start very early using promotion, using very different interactive and interesting tools, with the aim to motivate young children to start with the science and technology, and then proceed with the higher on the middle schools, high schools, to promote again the science and technology, so that we will have many new different study content and many different possibilities, so that the higher and high educational students will have possibility to work in different environments, and to have very practical possibility to make the dreams or make the ideas which they have come true. And this is a kind of this Maker Lab is one of really good examples of the transfer of the knowledge and transfer of the possible infrastructure which we have. There are also good systematic moves in Slovenia ongoing. We have these InnoGroup projects where there are a lot of possible trainings for the teachers and assistants. The student innovative projects for the society needs, and the creative path to the knowledge, Erasmus Plus projects, and so on and so forth. And I will just like to, for the end, I would just like to give you some good practice cooperation examples where our faculty cooperated with industry and other universities in Slovenia, where we work together with Gorenje, with Faculty of Mechanical Engineering from the University of Maribor, when we optimize the temperature fields. So the really concrete and very practical oriented work where students work there from both faculties together and solve the problems for the companies. Developing 3D printing magnets, Faculty of Polymer Technology, Faculty of Mechanical Engineering and Electrical and Computer Science in University of Maribor, together with Magneti Ljubljana, with Faculty of Chemical and Chemical Technology, University of Ljubljana and Helios, and so on and so forth. And I will just now like to show you one nice movie, really short one, how we made a kind of higher educational cooperation between our faculty of Mechanical Engineering, University of Maribor, Faculty of Electricity of University of Ljubljana, and Academy of Arts of the University of Ljubljana, where the students get the challenge to develop carrying bags for the beef jerky. And I hope this movie will go on. I hope you also will hear the sound. The whole video will show you that there was really good teamwork, and the students really make a really deep dive to this problem, to this challenge, using ideas, using communication skills, using different technologies and different materials to create a new material, which will be at the end, which will be shown.
Right hand, left hand, I'ma stand beside him. Got in my chest, so I am the pilot. I'm up here where the air is silent, no cameras or fencing, no pantomimes, no answers down here, but up there they might be. I cannot hear the sirens, I cannot fear the giants, planning on violence or planting some violence. Either way, these hands gonna land these panties, damn it, I am what I am, come find me. I'm running this game like multi-roll. I'm running this game like multi-roll. I'm running this game like multi-roll. Yeah, I got a parasite, me to raise it, upgrade it, ain't nothing funny. When I see myself like a parasite, I'm staring down dude gauges at 2020. No amusing the shit that takes shots of my image repeatedly. Dummy, that's shooting to get, but I know who it is and it's eating me. Guess I'm hungry, look, why do I love so much? I'm holding on to the world and ain't giving. I'm running this game like multi-roll. I'm running this game like multi-roll. Hey, I'm running this game like multi-roll. Ain't no superhero, ain't no cape of parent face your fear, you ain't no pain to carry.
So I think you were able to see that with a lot of work, common work, with a lot of discussion, with a lot of skills at the end, and the support from the teachers, students, assistants, a lot of creative ideas and a lot of creative solutions can be presented. And last but not least, an additional thing which I already spoke about it is that the teachers, we as the teachers, as assistants, we have to develop new methods and new ways how to give the knowledge to the students with so-called flipped classroom approach, where we should involve the students already in the pre-study so that when they come to the lectures, they are ready, and that during the lectures, we can really discuss the cases, and we have then the really good communication about the problems which will be discussed during during the teaching hours. So with that, I would like to conclude my presentation. I really thank you for your kind attention, and if there will be some questions in the next time, please just let me know. Thank you very much.
Thank you, Dr. Nardin. And now it's time for any questions, first from the live audience, if there are any. There are no questions in the Zoom chat either, so we will now finish today's event. We have reached the end of our conference, and I hope that you have enjoyed these 4 views of our eminent experts on the future of materials and on the materials of the future. And now allow me to invite to the stage Ms. Vesna Nachtigal for a few concluding thoughts.
Oh, sorry. At the end of this event, I would like to express my gratitude to all today's speakers for sharing their knowledge and experience with us. I would also like to thank the organizers of the event, SRIP Top, TECOS and the Josef Stefan Institute, in cooperation with the Ministry of Economic Development and Technology, Spirit Slovenia, DIH Slovenia and BTC City for the opportunity to be here with you today. Ladies and gentlemen, thank you for being with us, and I hope to see you soon again in person. Happy New Year and also Merry Christmas.
Thank you very much, everybody. I would like just to invite you to our next session, Circular Economy through Industry 4.0, that will begin shortly after lunch. For the people present here, I would also like to say that lunch will begin at 12 o'clock, not 11:30. So let us join you and let's talk further. Thank you very much, everybody. Thank you.